Alright, welcome to the fourth talk on Foundations of Mathematical Proof. Today I will be going over logical implications. So first off, I want to talk about implications, and we're going to let P and Q be statements because these are what we've been working with. So the implication if P then Q is denoted by P then an arrow pointing to Q. It's a new statement that receives truth values according to the following truth table. So notice if P is true and Q is true, if P then Q is true. If P is true and Q is false, then if P then Q is false. If P is false and Q is true, then if P then Q is true. And if P is false and Q is false, then if P then Q is true. Now, it's a little confusing at first for the when P is false, but think of it this way. Let's say I ask you a question and I say, if you get this question right, I will give you $100. And let's say that's what I say to you. So you get the question right, so that's P, and I give you $100. That's Q. I was telling you the truth, so if P then Q is true. But if you answer the question right and I don't give you $100, that's P being true, Q being false, then if P then Q is false. But if you get the question wrong and I give you $100, I didn't lie to you. I said nothing about what would happen if you get the question wrong. All I said is what would happen if you get the question right. So even if you get the question wrong, and whether I give you the $100 or not, it's irrelevant. We still give that value a truth value, because we only care about what happens if P is true. So here are some logical equivalences involving implications, and I encourage you to go and build the truth tables to actually see why these hold true. So, and these will become very useful tools when we go into proving things directly and by contrapositive and all that good stuff, but you really need to know these implications. So if P then Q is equivalent to not Q, if not Q, then not P. P then Q is also equivalent to not P or not Q. And not P then Q, so the negation of P and Q, is equivalent to P and not Q. Alright, now I want to go to if and only if. So it's a little different than just the same if statement, so let P and Q be statements. The implication P if and only if Q, denoted P with double arrow Q, is a new statement that receives truth values according to the following truth table. So if P and Q are true, P if and only if Q is true. If P is true and Q is false, P if and only if Q is false. If P is false and Q is true, P if and only if Q is false. And if P is false and Q is false, then P if and only if Q is true. So the way I like to think about if and only if is that you're going both ways. So it's if P is Q, then if P, then Q. And if Q, then P. That's actually a logical equivalence to if and only if. And so both directions have to hold. So it makes sense that if P and Q are true, then P if and only if Q is true. However, it's hard to see when both are false is true. But remember, when we were just going one way, if it was false, we said, oh, look, that's true. So when both are false, the implications are true both ways. And it's a little complicated to get your hands on this at first, but just go over the truth table, and I advise constructing a logical equivalence between if and only if, and if P then Q, and if Q then P. So here's some logical equivalences for if and only if. You'll probably see if and only if abbreviated with IFF. So here's the one I mentioned that I advised you to make a truth table for is P if and only if Q is equivalent to Q if Q then P, and if P then Q. We also have P if and only if Q is equivalent to P and Q, or not P and not Q. And last thing I really want to cover is tautologies and contradictions. I just want to go over their definition because they come useful later on, and it's good to just know what they are. So a tautology is a compound statement that receives a truth value of true for any possible truth values of its components. So basically, a tautology is a statement that is always true no matter what its components are. Likewise, a contradiction is the opposite. It's a compound statement that receives a truth value of false for any possible truth values of its components. So tautologies are always true, so you can pair the T's, and contradictions are always false. And these will prove useful later on when we do proofs by contradiction and so on. Alright, that's all I have for today. Thanks for watching.